So regarding to today's topic, I'm so excited to be able to invite Scott Fullman to give us a really interesting topic. Is making sense of text data with deep learning. So Scott Fullman is the SVP of Data Services at Tronc, where he leads a team focused in improving newspaper operations using data science. He is also the founder of Manifold Analytics and advisory firm. This is an advisory firm focused on investing in early-stage companies with products enabled by machine learning. Previously, Scott led PwC award-winning global analytics lab, which was responsible for using data science to help solve real-world client problems. Scott has an MBA with concentration in statistics from the University of Chicago Booth Schools of Business and a Bachelor of Science in Engineering from University of Illinois Urbana-Champaign. So let's give applause to welcome Scott to give us a great presentation today.
Is this on? Can you guys hear me? No. Nope. Do I just push it?
Yeah, just push it once.
Hello? Hello? All right, cool. Hey everybody, thanks G for the intro. Appreciate it. I'm Scott, and today we're going to talk about deep learning for natural language processing. Earlier I sent out the link to this presentation on the Meetup chat board, so if you want to follow along, you can go there, or it's just a bit.ly link, bit.ly PyData _. There's a ton more information that I won't go through today, so you can use that later on. Also, the code to recreate everything that I talked about today is on GitHub, so feel free to check that out later on, use it, adapt it to whatever you need. Cool. So, let's see. Yes. All right. So we already went through the bio. I work at the Tribune doing data science. And so I won't go through everything. The one thing I will shamelessly plug is I also work with a bunch of startups here in Chicago, all of which are hiring for data science and data engineering positions. So if you're interested in any of that stuff and you like to work with text data, feel free to do that afterwards. Also, one of the company's data science leads is Keras. If you want to raise your hand real quick, if you're interested in working with text data, reach out to him as well. Cool. So let's jump into it. So today I'm going to do a couple things. The first is answer the question, why do we want to use deep learning for NLP? And kind of the opposite of that question also, which is important, when don't we want to use deep learning for NLP? We'll go through a couple of examples and build up kind of a framework to build deep learning models for natural language processing. And then ultimately kind of demonstrate the power of transfer learning and being able to take lots of data from one task and then pull it over to solve another task. I am not going to be able to get through all of deep learning for NLP in 45 minutes or whatever, however long this talk is. So what I tried to do is just give enough knowledge to get started. There's obviously a bunch of stuff that I'm going to gloss over. So I've designed the presentation to be two-dimensional, I guess. If you open it up, you can go right to left, and that's what you'll see on the screen. And then a few of the slides, or a lot of the slides actually, if you click down, you'll actually see a bunch of other information, resources, and links to interesting things to do. So that's how this is set up. So what is deep NLP? At the highest level, all we're talking about really is using neural networks to accomplish common natural language processing tasks. But kind of the key thing here is that we want to take advantage of the way that deep learning and neural networks process the data automatically and the representations that they create of text data, because they're very good at doing things in a generalized manner. So one of the things that Keras is, what are kind of the main motivations, and performance always comes to mind. Yes, it's true that you can get better performance from a deep learning network on NLP tasks, but I caution that shouldn't be your primary motivation, or at least not the first thing that you think of. Really what we want to be kind of motivated by is these last four bullets. So moving from human design features to kind of automatically learning and representing the way that data is structured. The second is a huge one that we'll touch on with an example, which is transfer learning, which is where you can take all the data you have for one task, build a model for it, and then reuse that model for another task. And generally, your first set of data is a huge amount of information and a really good model, and then you use it on another model, which is usually has less labeled data. And then the last two are pretty interesting. Deep learning is very good at multi-input, multi-output models. So if you have many types of data already in, like for example, I saw there's some talk in image captioning coming up, you're putting in a picture and maybe some other information, you're getting out something else. Or if you're training a model to do two things at once, what we found is that actually the results for each individual task are better than two individual models doing something separate. So that's kind of the main motivation. The recap there, performance, yes, you get something better than if you use some traditional techniques. But really what we're trying to do is take advantage of transfer learning and some of the different representations. So what's possible with the usual stuff when you talk about natural language processing? So classification, sentiment, attribute, part of speech, those types of things. Today we're going to talk through a sentiment example and a language modeling example, which is basically coming up with a way to kind of represent the way the order of words come out. Some of the sexier stuff that has been happening recently is summarization, translation, dialogue generation. All this stuff is really cool, but the kind of key point I want to make is that usually the language modeling task is the first step to a lot of that stuff. So when you come out of the presentation today, you'll have kind of an understanding of what that is, and then be able to apply it to something that's more complex. So one last thing before we get into it, quick warning. Please build simple models first. Don't start with deep learning. Don't fire up Keras the instant that you hear about text data. There's a huge resource and time trade-off when building these models. So I want to caution that please don't take away from this presentation. The first thing that you should do is build a deep learning model. And in fact, if you're not taking advantage of either the data representations or transfer learning or multi-input or multi-modal data, you probably don't need deep learning, and you should just move on to the need. So. Okay, so let's jump into what we're going to talk about today. We'll do a quick warm-up example to show how a neural network works and standardize on terminology. We'll build something with network in Keras to show how things kind of come together. Then we're going to build up to an actual text example where we look at IMDb reviews, and then we're going to judge whether or not that review has positive or negative sentiment. It's kind of a standard benchmark in NLP. And then the last part of the talk, we're going to actually build a language model using a much larger data set and then apply it back to our second task. So we'll see if we can actually beat what we did in the previous section to kind of show that that's actually useful. Cool. Actually, let me just ask before. How many people are pretty familiar with working with neural networks? Good enough. How many have used text data before? Good enough. And then, has anybody built stuff with Keras? Okay, cool. So let's kick it off. We're going to do a quick warm-up example, just to show what I'm talking about when I say model, layers, activation function, and so on, and then how it all comes together in a quick bit of code. So I made up a bunch of data. Each data point has two dimensions, an x1 and an x2, so you can think of that as your features actually. And then each data aligns to one of four categories. So if you plot that, hopefully you see a pattern, unless, sorry, I had it pretty colorblind. Basically what's happening here is there's four clusters of data. Each dimension, x1 and x2, are plotted in x and y. And then the color represents the class associated with it. So you can kind of clearly see a pattern. And basically what we want to do is train a network to say, when I put in the data point that's function 5 and function 5, it should show up in the other class. Pretty straightforward. So to do that, I just want to go through some terminology. When we build a neural net, the first step is obviously just getting our data together. And we're going to format it so each row is a feature vector, In our case, we only have x1 and x2. We can add n-dimensional feature vectors though. And then we're going to push it through our model. And in this case, the model is going to be made up of a series of layers. So A1 is a layer, A2 is a layer, N is a, and 1 to n layers. And then each layer is kind of built up of two functions. One is a set of weight transformations. So we have this weight matrix that we multiply by the previous layer. And then we push that through what's called an activation function. And that's where you get kind of the nonlinearity or the kind of coolness that happens with it. We take the output from the first layer, we push it into the next layer. We take the output from that layer, we push it into the next layer until you get to the end. And then that last layer essentially outputs a vector that you hope looks like what you're trying to predict. That's all there is to it. So, once we have that, what we need to do is measure essentially how poorly we did. Because we initially started the model off with randomized weights, we're going to push our data through and then a bunch of garbage is going to come out. And to do that, we're going to use something called a loss function, which basically just measures that incorrectness. And then we're going to take a second step, which is kind of the most mathy, but most important, which is because we've just chained all these functions together, and all of the functions that we have, we've calculated a derivative of, we're going to take the derivative of that loss, or how wrong we were, with respect to the weights. And what that actually gives us is the idea that for each weight, I know how much it contributed to how badly we did, which is a super important concept. And then use an algorithm called backpropagation to essentially push that information back up the chain, update your weights, and then go round and round until you stop making improvements. So I'm going to stop there. Any questions? Am I totally out of place here? Okay. If you didn't get that, don't worry. The key components are there's an input, there's a model, which is made up of layers, and then the layers are made up of weights and activation functions. The data is transformed. A loss function measures incorrectness. Optimizer starts pushing the changes back up, and we just circle around. So we're going to use Keras to take that kind of theory or concept to encode it into a model. So if we think back to our warm-up example, we had a feature vector of shape 2. So we had two inputs, x1 and x2. And the way that we get that into a model is to use an input layer. We pass in the shape for the first dimension, which is 2, and then we leave it blank for the second because we want to be able to give it a flexible amount of data. We can give it 5 rows or 100 rows or 1,000 rows. The next step is to kind of chain things together. So in this case, we had A1 feeding into A2. In this, what we're going to actually do is take our input data and put it into the next layer, which we're going to call dense layer. Dense layer is made up of a dense layer in Keras, which basically just means that we have weights that are associated with every input. We're going to choose a size to make this vector. In our case, we're choosing to make it 8. And you can get into a bunch of different reasons as to why you choose a smaller or bigger one, but we won't touch that yet. And then we're going to choose the activation function that we're going to use to create a kind of nonlinear event. And in that case, we're going to choose something called a loop, which is a pretty common standard thing to use. And again, I won't get into that, but if you go down in the presentation, there's a bunch of stuff in it. Now, the first tricky thing we're going to encounter with the kind of syntax of Keras is they treat objects as functions as well. So you get this weird double parenthesis where it's essentially a dense object, and then we treat it as a function, and then we pass input data to that object. So a dense layer becomes the dense object that then takes the previous layer as an. Does that kind of make sense? When I looked at that the first time, I was like, that's not how and then we're just going to go down the line. So our next layer is going to be called output prediction. It'll take dense layer, and then we're creating this kind of chain of events that happens. And in our case, we're going to have 3, but we can start adding as one this week. In the next section, we can create our model. The model's pretty simple. You create an object called model. that takes inputs. In that case, we have input data as input, outputs are output prediction. And then it can kind of work behind the scenes to actually chain the whole things together. So dense layer is actually included there, and it knows how to go from input data to output data. Finally, we compile everything. We give it a loss function, an optimizer, and a metric for its track, and we have a model. That's it. So, Keras is a kind of, I guess, super high-level abstraction of a deep learning framework that relies on other libraries to actually do all that computation, where we push the data through, we compute the loss function, we calculate the derivatives, push the gradients up, and things like that. In this case, we're using TensorFlow underneath, and so that's kind of the relationship between those two libraries. But the nice part is, just like with scikit-learn and stats models, you can take a model, run a .fit, you pass your data, x and y, and then there's kind of two other things that you want to pass along with it when you train. One is called the batch size. The batch size is basically how many pieces of information do you want to put in before you update those weights. And then the second is epochs. Epochs is basically how many times you want to go through the entire data set before you call it. And so if you hit enter and run this, you'll start printing out the results. And what you'll see is two things, loss and accuracy. So our loss starts going down, which is basically how incorrect were we. And so if it goes down, that's good. We're doing less incorrect or more correct. And then accuracy, which is basically saying, of the accuracy of the model as it goes up. So cool. And if you plot that over 60 epochs, you can see the blue line is accuracy. You get to around like 98% or something, and then the loss is the yellow line, and it goes down again. So that's kind of the warm-up example. That's how you kind of do a quick model of Keras and go from there. Any questions on that? Yeah. Yeah. Sure. Which you? Actually don't know how to do this. There's something recording me right now.
What are you looking for?
Oh, actually.
Oh yeah, I think it's consider it like a monitor on the other side.
Perfect. Okay. Is that better? Okay. So now let's actually do a text classification because that's what we can do. So we're gonna do a binary sentiment classification, and basically our input is a text movie review from IMDb, and our output is going to be a guess as to whether it's a positive or a negative score, as defined by whether the rating is 7 of 10 or better. We have about 50,000 negative reviews, split evenly between test and train, and then it's also split evenly between positive and negative. And you can see an example here of a review that I pulled. It's got all kinds of things like grammar mistakes, misspelling, markdown included, all that stuff. This particular one, this guy's ranting about The Apprentice and Donald Trump. I wonder how he's doing now. The last thing we want to track is the metric and how we're going to kind of grade ourselves. And instead of using accuracy, I'm going to use an F1 score, which is just a blend of precision. Cool. F1 you can think of as like, it's not quite an average of precision and recall. Let's say for example you have a skewed data set where 90% of your examples are positive and 10% are negative, I can get a 90% accuracy by guessing they're all positive. With F1, if you blend precision and recall, your recall is going to be higher than your precision is going to be. So then it kind of gives you a better idea of what you're doing. So here's the roadmap for this task. What we're first going to do is establish a baseline with a simple model. Then we're going to prepare the data for the deep learning model. We'll build our model, and then we'll train for the measure. See how we did relative to the baseline. So I keep harping on this, but it's super important. Build a simple model first. There's a blog post down below that I love called Start with a Stupid Model. I don't actually think it's a stupid thing to do, or it's a stupid model. Its baselines really help us learn about the data, build features, interpret it, and the thing is, the cycle is really fast. So you learn a lot very quickly versus the deep learning and waiting around one time for The other thing is, you could be done now. If your model achieves the performance you need, then just move on to the next task. Don't waste your time building training models. And obviously, you want to consider production. You don't want to just give it over the fence to Jeremy and say, good luck with that. So let's build our baseline. For anybody that's used scikit-learn, you can probably most familiar. We're basically doing two things. One is to take our text data, break it into words, and then count how many times each word shows up, and turn that into a really big feature vector using that TF audio vector. We do some normalization in there, but you can think of it just as a word count. And then we run it through logistic regression with rich regularization. So it's very simple, but to be honest, this solves like 80% of text classification problems, and you don't really need anything more. So if we push that through and we train it, what do we get? My box is off for some reason. But the bottom line is that we get a F1 blended of about 0.87. So that's pretty good in that our random baseline is 50-50, so we're getting way above random. And then the other thing is, this is now our kind of get out of bed today, we're kind of deep learning threshold. If we can't beat 0.87, there's no point in kind of working with it. So that's the baseline. The next step is, yeah.
Quick question. So these, you talk about doing like these models first.
Yeah.
And then, you talk about using models first. The question is, when do you know that your harder models don't work?
Yeah. The short story is that if you're using, if you're not using transfer learning, basically pulling information from outside the label data that you have, you don't want to use it. That's the short characteristic. So, prepare the data. If you worked with natural language processing before, you've probably done some of this stuff where you lower everything, stem it, lemonize it, use anagrams, maybe you insert a part speech as a dependency model. With deep learning, we're not quite throwing that all out the window, but what we're trying to do is get as close as we can to the raw data, and then just push that through the model and let it compose the features automatically. So through the layers that we build, it's going to start to figure out that now the verb together means something, or the New York Times together means something different than New York and Times independently. So the key thing here is that we're going to move from a count-based vector, which we did in the baseline, to creating sequential inputs. So we're going to record that one word came first, then the second word, then the third word, and then we're going to feed that into the model. And that's kind of the key distinction, is that these models take advantage of order, which is great. I won't go through the rest of this stuff. So this is a terrible slide, but I couldn't fit everything on here without going off the page. So the way that we prepare the data, first thing we're going to start off with our review, which is this one big string. The second thing we're going to do is run it through a tokenizer, which basically breaks up that string into pieces that we'll call tokens. Most generally, they're going to just be associated with words or punctuation. In this case, we lowercase everything, which makes our vocabulary much smaller, so that when things start the sentence, like the something something, that's a capital T, versus the middle of the sentence where it's I went to the store is a different word. They all just get merged into one. Then the next bit is kind of more specific to the deep learning model. The first thing we have to do is take each individual word or token, and then turn it into an integer representation. So basically, I turns into 14, love turns into 453, dog, and so on. And the reason that we do that is that we need to create a map between our words and something else that we'll get to later. So that's basically kind of the intermediate step. And then the last thing is we need to make all these reviews the same length. So reviews vary in length, obviously. So we need to set a kind of a threshold. Let's say it's 200 tokens. And if the review is shorter than that, we add a bunch of zeros. If the review is longer than that, we truncate it and hope for the best. You can obviously kind of look at how long your reviews are on average and then make that up. So that's prepping the data. Yeah? So it's primary you can change if you want to. There's different theories as to why this works better, but I don't think it is convincing. So I don't know what it is. Okay, so we've prepped our data, we built our baseline, and now we're going to build a model. In addition to the kind of dense layer that we talked about, there's also different types of layers that are specific to NLP tasks that you can use in layers. The types we're going to talk about today are embeddings, convolutions, recurrent neural nets, or in this case LSTMs, and then attention. Let's walk through this kind of step by step and build up the understanding, and then talk about what each one does. So first up is embedding. If you think back to our data that we feed in, we're basically just giving it like a 5 and a 14 and a 453 and whatever else that stand for those words. But the model has to figure out what that actually means, because in a sense that's categorical data, right? You're just assigning a bunch of random integer representations. So we normally deal with categorical data, maybe by one hot encoding, or we can do what we did in the original baseline, and do some type of count or TF-IDF vector. But unfortunately, those are just all too big, because we end up with like a 200,000 dimension vector, and then also they don't allow for generalization. So you can't look at a vector for a car and a vector for automobile and then kind of see that they mean similar things, because they're essentially a bunch of zeros with a 1 representing that particular thing. So long story short, the way that this problem is solved is that we use distributed representation of tokens, or word vectors, which you may have heard of. Word vectors are basically kind of a dense representation of a word, maybe, let's say, 100 dimensions or 200 dimensions rather than 200,000. And instead of being all zeros and a 1, each dimension contributes a little bit to the meaning of the word. So you have a much more compact representation. So where do we get these word embeddings? There's lots of different ways to kind of create them, but it all boils down to starting with a very sparse representation and then doing some dimensionality reduction. So you could say, look at every sentence, develop a co-occurrence matrix of when this occurs, that occurs, and then do PCA or something like that. The more sophisticated model is going to look at something like the picture here, where given a word, like banking, let me try and predict the words around it, and then I'll use the weights from that model as my representation of those weights. Again, there's a bunch of more information down below if you want to do that. We're actually going to cheat and just download some that were actually already trained on a much larger data set. So there's a couple out there that are commonly used. Google News Vectors, which is like on a billion news stories or something, or a billion words, is the one that chose. Okay, so we have our word vectors. Now we need to push them into the model, and we're going to do two things. First is on the left, we're going to come up with kind of that second or third column in that map, where we have a word, an integer, and then a vector all kind of tied together. And then that third column together becomes what's called our embedding matrix. And basically, it's a matrix of word vectors, and then each row corresponds to the number of the word that we picked before. And then on the right side, we're going to use the embedding layer in Keras to actually bring those word vectors into the model as needed. So we start up top with our string, then we tokenize it, we have integer representations, and then finally that blue section represents the embedding layer, which is basically for every word, there's a word vector. Cool. So how do we drop this in the model? Similar to the one-loop example, we have an input, and then if you skip over the nice stuff and the oopsies, we have a prediction at the end and a model. That hasn't really changed. The only thing we've done here is add an embedding layer instead of a base layer. We have to tell it a couple things. One is the vocab size, the output dimension, which is an embedding link, and then give it those word vectors, which is that embedding links matrix that we got from the previous slide. And then just tie it back up to the input sequence. So that's our first step in creating this model. The next thing we want to do is use a convolutional layer. So if you guys have used image recognition at all, there's Convolutions are very popular for that. But you can actually also use convolutions for natural language processing as well. You can think of a convolution as basically a way of applying a filter to a matrix. And if you can kind of see through that filter and something pops up that gets you excited, you mark it down. There's a GIF that people use to kind of explain it. I don't know that one, but I'll show you another example in a bit. So instead of running this over an image, we're actually going to run this over our embeddings for each word vector. And hopefully what that does is kind of turn things into a more useful representation of the data. So what does this kind of look like? The top half is just the same thing that we had before. And then you add a convolutional layer. And there's kind of two things that we look at with convolutions. One is called the kernel size. So how many words do we want to look at a time? And then the second is the filter size, or how many different filters do we want to have scanned over the data. So in this example, the orange box represents the convolution at a step in time. The kernel size is going to be 2 because we're looking at 2 words at once. And then the filter size is going to be 3 because we have 3 dimensions in our convolutional layer. So if you kind of animate that, it looks like this, where each color is a different filter, and then it'll attribute different things to each row if it gets excited about what it's using those things. So again, how do we add this to our model? Pretty straightforward. So after the embedding layer, we add a convolutional layer, and then we just tell it which convolutional filter size we want and then which kernel size we want, and we tie it back up to the embedding. In practice, instead of 2 and 3 dimensions, usually you're going to have about somewhere between 50 to 100 filters. And then the kernel size that works best is usually 3, 4, or 5 words at a time. So that's what we're going to do. Cool. Third layer we're going to deal with is a recurrent neural network, or a recurrent layer. And these are kind of the most commonly associated with text layer. Essentially what they allow you to do is look at things in a series or a sequence and keep track of what you've seen in the past. And the way that they do that is instead of having just one input in the previous layer, they actually have 2 inputs, the previous layer and then the previous time step within that layer. So I first have to compute this A, and then I feed it in to this A with the next input data from the previous A. So when we add that to the model, this is kind of what happens. So each time step, starting with the first one, gets fed into the LSTM. Then the next time step gets fed in with the previous representation of the LSTM, and so on, and you go kind of all the way down to that bottleneck point. What's cool about this is that an LSTM can help you do things like, let's say I have a review that says, I really like the acting in this movie, but ultimately I can't write anything. Whereas a convolution would say, I really like, and give a thumbs up, and then say, I can't recommend, and give a thumbs down. It would be kind of neutral. An LSTM can keep track of the original really like, and then the deviation later on, and say, ultimately, this person decided not to recommend anything. The cool thing about this is that you're pushing all this information to the bottom right, and you come up with this kind of final vector representation of the input. The problem is, in practice, it doesn't really work. So the amount of information that you're trying to squeeze through this model and then push all the way through the time steps is just too much to represent in that small vector. So we're going to use the attention layer next to kind of solve that problem. So similarly, we just add it to the network right underneath the convolution. Bidirectional just means look at it forward and then also look at it backwards. So normally it just looks at it forwards. Okay, so attention. So the problem we have is that we're trying to push all the information into the last LSTM hidden state, or last vector. But what attention does is say, kind of similar to what a human does. You scan through a sentence, and some words are interesting, and some words are just filled. So attention basically does that, but in math form. It can scan through all the time steps in the LSTM, or the previous layer, and say, this one's important, the rest of these disregard. and it'll come up with kind of a weighted average of all the vectors. So if you put that into the diagram, now you're taking the output of every LSTM, and then you're taking a look and saying, do I care about this, or do I want to weight this very low? Come up with a weighted sum, and then you have a vector where you scan through everything, picked out all the important stuff, and then summed it up. So we've put together all four of these layers. The last thing we're going to do is take that last output and then run through our classifier, very similar to what we did in the warm-up example. There's a dense layer, and then the softmax at the end, which creates is it positive or negative. So that's building a model. It all comes together like this. We put the attention layer right after the LSTM layer, add a dense layer, and then have our prediction at the end. So, what happens when we actually do that? We get results with an F1 of 89. So if you remember before, our baseline was 87. So 89, not bad. But I hope I didn't, bring you out of, a half-hour presentation just to get slightly better results. So what we're going to focus on from here, now that we've built up the kind of terminology and knowledge of the layers, is how do we take a different task with a lot more data and then use it to solve our task here. And that's going to be a combination of language modeling and transformation. So let's jump to that. So, like I said before, one of the huge advantages of deep learning models comes from the ability to generalize features given a bunch of data. These models could have millions of weights, and if you don't have millions of examples to give it, it's not going to learn that well. And so what we want to do is find a way that we can take advantage of all the text data that we have out there, learn something about it, and make sure that we can apply it to a new task. And the way that we do that is to train one model, and basically cut off the bottom of that model and glue on the original model that we tried to do before. So a starting point for most NLP tasks is to do this using a language model. Language model is basically answering the question, if I give you a series of words, what word comes next? So if I say, like, who are the dogs, the model better say something like out with a high probability and in with a much lower probability. And because we only need just strings of text to train this data, we can use all the billions of examples that we found within. So how many millions of billions of sentences are there with billions of words? As long as we get access to something that's kind of close to the language we're using to ultimately answer our task, we're in good shape. So let's actually do that. We're going to find a bunch of stuff that's kind of similar to our domain. And rather than using IMDb, we're going to actually go out to Amazon, and you can download a data set that has 1.7 million reviews, text data, summary, user information, and so on. I think it's from the 1987 to 2012 or something. So that UCSD compiled. And then we're going to build a model that basically predicts the next word on all those reviews with a few minor tweaks. We're going to add a little bit of prioritization, which I highly recommend checking out some of these below. Again, I won't get into that. Instead of using one convolutional layer, we use 3. And then the key here is we're actually going to do a multitask model. So we're going to ask it to do 2 things at once. The first thing we're going to ask it to do is look forwards in the text and guess the next word. And then we're going to create another branch of the model that looks backwards in the text and guesses the previous word. So that's pretty straightforward. Fair warning, if you do this at home, it takes about a day to train with a GPU. Or you can go on Amazon and get a GPU spot instance and do it in 4 hours. So here's what that kind of looks like in picture form. Similar to what we had before, an input, our embedding layer, dropout is just a regularization parameter, our convolutional layers, and then 2 LSTMs. One is looking forward, predicting the next word in our dense layer, and then one's looking backwards and predicting the previous word in our dense layer. If we set that up in Keras, it's pretty straightforward. all the way up until this concatenate, where we glue together all our convolutions. It's almost the same. Here's where things kind of get different. The first LF, or LSTM forward, is taking the output from the concatenate and then passing it to an output where it predicts which word we're looking at. And that's where that branch of the model ends. Then there's another branch of the model that starts, again, from X, which is the concatenate, and then passes that to a dense layer and creating the word backwards. And you'll see go backwards equals true. All we do is just say put that in the and then the other thing here that's interesting is that creating a multitask model is as simple as saying put in your input and then do two things rather than one. And you can do the same with multiple inputs and multiple outputs. So if we do that, here's what we end up with. The top is original review that came from the Amazon dataset. So that's the tokenized text. I think it's a review about Christmas Carol. And then here's what comes out of it. The letters are off. I tried to highlight all the stuff that changed. But instead of saying the classic Dickens tale, it says the classic Disney tale. Probably because Disney shows up more often than Dickens in the dataset. Same thing with Scrooge, and I think they get Henry Nicholson. Yeah, it says Henry Nicholson instead of Henry Nicholson. Probably because Nicholson is more common. But what you see in this is that it actually does a pretty good job of predicting the next word. So if I gave you a string of text and then said predict the next word, you could actually learn something. And what this indicates is that all of the layers that we created have learned a pretty good representation of the text data, which is kind of cool. So how do we actually use this to do something with our IDE data? The answer is we just basically cut off the bottom and then glue on new layers. So in the top half, it should look familiar. It's exactly what we talked about before. We have input, embedding, dropout, convolutions, and then concatenate. And we're going to initialize the model with those same weights that we learned for the language model. And then we're going to glue on the bottom half of our previous model, and we'll start with random and see what happens. So then we can just push back in our, So how do you do this in Wix? Even more straightforward, actually. So you load in your language model, which is something that you previously trained. And then for input, we're actually going to do something different. Rather than passing in a new input layer, we're just going to say grab the input layer from the language model. And then once we're moving on to the next step, we're going to say, okay, create our LSTM, which is this bidirectional operator data line, starting with the new layers. And then instead of passing it the input, we're actually going to pass it the layer from the language model where we're going to start. So we're going to go -5 in this case, so the fifth layer up from the bottom in the language model, and just glue those two together. And then we throw in our attention and our dense layer and classify it, and we basically kind of combine those two things. So very easy to kind of use everything once you train it. And then the model weights from the original language model will be automatically kind of transferred over, and the new layers will be randomly initialized. So what happens if you do that? Our F1 boosts up to 91, which coming from 87 is not bad. We have essentially reduced the error by a third in terms of what was left. And we didn't even really try and tune anything. The current state of the art for this task bumps this up to 0.95. And essentially they're using the same general approach, just with a little bit more data, or a lot more data actually. And then a few tricks with the way that they kind of fuse and increase layers when you train. But the net here is that this is kind of the approach that everybody's using for computing benchmarks with regard to deep learning. And so just to show that this was not kind of a one-time fluke thing, I went out to Chicago and I downloaded data from the competition from a few years ago that was similar, so it was movie reviews. But in this case, it was rating 1 to 5 versus just positive or negative. And I trained the exact same model with this data. I didn't change a thing. And that score that you get puts you in the top like 4% of the leaderboard. So it's transfer rating in the true sense transfer learning in the true sense, that we can just take this, lift it, and push it to a similar task and get a really good result. Finally, to kind of push this to the extreme, Salesforce just did an interesting thing, where they actually trained the model to do 10 things at once, summarize, create a question-answer system, translate, and something else. And then kind of did a multi-output model where they asked things to find different entities within the text, answer all those questions, and so on. And this model actually outperforms pretty much everything that's out there in terms of what's available. So the idea here is that the more things you can put into the model, the richer the data set, the more tasks that you can add, the better results you're going to get in terms of seeing the ultimate end results in your task. So that's pretty much it. Hope you I gave you kind of like a high-level overview of getting started. So you start with simple models, move over to deep learning if you can take advantage of transfer learning or data representations, or multi-input, multi-output. There's obviously tons of stuff we didn't cover in this talk. There's a bunch of courses out there that help you really better understanding. My favorite is Stanford's CS224N because they have all the assignments, all the examples, and all the YouTube lectures on YouTube, which is great. And then all of this stuff is actually on GitHub, so you can actually reach out and use it. So that's it. Any questions? No question? Yeah.
Yeah, for the earlier slide, like the second slide with show that the relation function is the relation function.
Over here?
Yeah, that's the one. So the actual program.
Yeah.
You said something about so there's 4 arguments. What arguments?
Yeah, sure. So basically that's the size that you want to make that vector. So if we want to make A2 8, then we pick that as the output. The 8 is somewhat arbitrary. That's essentially the layer that kind of learns what's going on. So the bigger you make it, the better it's going to get learning, the better it is for illustrating. The last layer, the 4, has to be 4 because we have 4 classes. So we want a vector that will determine which of those classes. Yep. Yeah.
Hi, it was a great presentation. I appreciate all the insight. When you split at the end of the neural network, you had a layer that was called time series. I was wondering, what does that do?
Sure. I think it's time distributed.
Time distributed. That's one.
Yeah, so that's a way to cheat, and basically instead of creating a, let's see if I can get a good picture. Yeah, instead of creating a dense for this one, a dense for this one, a dense for this one, and a dense for this one, it creates a dense for all of those in one. So it's just predicting the next word.
Thanks.
Yeah.
I have a question. Why wouldn't you use, when would you not use, deep NLP for classification?
The shortest answer I can give is if you're not taking advantage of transfer learning, don't use it. So if you don't have another data set that's much larger than your labeled data set, where you can either train a language model or as a similar task and you can train a classification and then transfer that model over, don't use deep learning. Does that?
So you should have a bigger data set, I'm going to say.
Yeah. So unless, in this case, because Amazon data set was 1 million some reviews, we can learn a lot from that data set and then push it over to our IMDb data set, which is only 5 or 50,000 or whatever. But if you have a small amount of labeled data and you have no way to incorporate external information, probably shouldn't use deep learning.
What would happen in the case of one class infiltration, you have a really unbalanced data set?
Yeah.
Can you use XGBoost?
Sure. You can. I would recommend starting with the simplest model that you can, and then kind of walk up the stack. Yeah. Yep.
Hi.
Hey.
Very nice presentation.
Thanks.
My problem is, like, I'm working with attribution extraction right now.
Okay.
And there's a lot of interest in using deep learning. And I said, no, this is a commercial project, you need really low error rates. And, so how about something simpler like random fields? So I'm wondering, do you agree with that? Or do you think that this problem is a point where maybe I take longer using random fields to get the same level of accuracy?
Yes.
You can just take go on to your
Sure, I guess two answers. One is that, so you mentioned your requirements around having to have a very high level of accuracy. So I think that's a kind of business decision, basically, right? So how much time do you want to spend on this in order to try and match that? And I would caution that debugging, building, and tuning these models takes a really long time, and the cycles between them are long because you have to train everything. So it might not be the right choice. However, I would say that in another project, we're building entity recognition systems where the top half of the model are similar to what we've had here. We get to a kind of representation by word, or a vector every word. And then you can actually apply a random field at the end to the data that you've created using the neural network. And if you do something like transfer learning, where you learn a really good representation of that data on an external data set, you may be able to get a really good representations that you can then feed into your random field and potentially get better performance. So I don't know if that's the answer, but maybe.
Was it to predict the rating of the user given the text that the user wrote, or to predict the rating of the movie given all of the user's text?
Yeah, sorry, I should have clarified. So it's to predict the rating that the user gave to that movie, and not the actual rating, but just whether it was above 7.
Okay.
Oh, hey, yeah.
Yeah, you mentioned that one of the more the important aspects of a lot of use NLP when data sets were like bigger data set and small one.
Yeah.
How do you know if two data sets are transferable?
You don't. It's kind of like a
because, like, for example, like Adler and then movie reviews.
Clear match.
Different communities have different ratings. Like some people think 3 stars is a good restaurant, while others think 5 stars.
Yeah. So I guess there's no hard answer. I would say one thing that you can do is look at the data that you're looking to transfer from, and take a look and say, okay, how many of the words that I see in my original data show up in that data that you're looking to transfer from? If there's a good kind of overlap, and that data is an order of magnitude bigger, I would say go ahead and train a language model and just try it. If you start to see that the way that people describe things and the terminology or the jargon or whatever is totally different, and there's not a lot of overlap between what people talk about just in terms of the words they use, that's probably a good indication that maybe you should look somewhere else for different data. But it's a judgment call in terms of, is it worth it? Yeah.
And very good presentation. So I have 2 questions.
The first one is, okay. So the first one.
That's okay.
Okay. Yeah. Okay. So the first one is in the second semester, right? So you start with all the business people, right? You didn't actually start with the feature.
Oh, in the Amazon language model?
Yeah, in the second one started with the business word, right? So you just start from here. You start from the
Oh, the word vectors. Yeah, so I think the question is, did I start with the word vectors as the input? Right. Yeah. So you feed in to Keras the integer representation, and then the embedding layer just automatically grabs the word vectors. So you're right in that what the model is using is the dense representation of the word. But there's a little bit of code written, so it makes it easy for you to not have to write something that translates between the two.
The second question is actually, so under the HANA, so what models you want that very simple model to like many layer model? For example, I know what models you can add the composition layer to standard way nowadays.
Yeah. Yeah, sure. So I think the question is, what motivates you to kind of use these layers as the thing that you use? Right. So this is kind of a combination of standard practice in terms of the LP, and also kind of learning in terms of what works or seems to work. To be totally honest with you, in a lot of cases, you can just get rid of the LSTM. You don't need it because if you don't have sequential problems where you're building something up or gating something later on, the convolution does a really good job, and it's way faster because you don't have to wait to compute every step. But yeah, basically it's kind of the standard stack, I guess. You'll see a lot of people say bi-LSTM plus attention. That just means the bi-directional goes both ways plus attention. Yeah.
Yeah, one thing you mentioned initially is that I guess you took that text focus and you released that very
lowercase word example. Are you actually doing it? Because you mentioned shortly after that it's better when you're on that to not do that initially.
Yeah. So the short answer is no. I'm not doing that. The only one of these things that I'm doing is lowercase. I don't stem anything. I don't monetize anything. We're not adding dependencies or part of speech. The idea is get as close to the source data as you can, so that you can learn an end-to-end representation within the deep learning model, rather than trying to say, okay, I'm going to hand design when I see New York Times, then I put them together. Because those features are ultimately good, right? You can't do that for every newspaper, or every new newspaper starts, then you don't have any users. Yep. Yeah.
Have you seen cases where the caps might help? Like, for example, when people use all caps, that might indicate their feelings?
So interestingly, that's a good use of special tokenizer. So, but the way that you do it is you still lowercase the word, but you add a special token before it that says like all caps. So you know that the next token that comes was originally all caps, but you don't have to create a new word vector for the caps version versus the original version. Yeah. Yeah. Yep. Yeah. So in this first. Yes. The answer is yes. You do get better results because what you're doing there is similar to transfer learning. You're taking all this information from other data sets and trying to push it into your own model. And if you go down in here, there's different links to, if you want to train your own, you can use Jensen. There's pre-trained Google News vectors. There's Glove vectors, fast texts from Facebook. And then there's a whole 2-hour lecture on creating word vectors from Stanford, which is really good. So, yeah.
Do you mind if I grab the mic? Just because in the back sometimes it gets hard.
Use the convolutional neural network with the LSTM and attention. I'm guessing this was because you got the best result. I was wondering what's your opinion using bidirectional GRUs instead of LSTMs?
Yep.
And if you try that.
Yeah, sure. So the question is, did I use a GRU instead of an LSTM? GRU is another version of a recurrent neural net that is a little bit simpler than an LSTM. I didn't try a GRU for this particular task, but you definitely could. It's one of the things that you should tune and try. In empirical kind of evidence I've accumulated over the years is that you get pretty close with both. So, yeah.
I'm wondering if for the proper convolutional,
Yeah.
required to choose the kernel settings. And how many words you want to look at what?
Yeah.
So based on your experience, how you going to each time how you going to
Yeah. So the answer is, the question is, how do I choose the kernel size or the filter size? And the answer is actually, there's a paper out there that basically went through and tried to do every iteration of version of this. And what they found is that you should actually use a few different window sizes. So try one layer with 3, one layer with 4, one layer with 5. And each of them should have a filter of somewhere between 50 and 100 filters. And then you just glue them all together. So.
would that make your model more complicated?
Yes. The short answer is yes, it does make it more complicated. But I'd be less worried about it for convolutions because convolutions are very fast to compute, so it's not adding a lot of training time. So the LSTM would. Yeah.
And just to follow up, for her question, isn't that a language? Like, doesn't that depend on what kind of language? For example, if you're using, I don't know, if you're doing text analysis on computer science versus law.
Yes.
So is it like computer science, you're going to have like chunkier, multi-word terms. Whereas in law, you might have more particular, I don't know.
Yeah.
I don't know.
Yeah, so the question is basically, does your domain text matter in terms of how you pick the kernel size and filter size? The answer is totally. If you do Mandarin, it's going to be a lot different because there's way more characters and the words look different from the way that they're represented in English or another language. That particular result was just for English language text. Definitely, if you're doing something with like computer science syntax or whatever, it's going to be different.
Just to clarify, all as well, you were doing concatenates, branch off, and then concatenate there?
Yeah, sorry. Yes, the question is, did I, does blue mean concatenate? And the answer is yes.
Hi, are there certain techniques you go to when someone asks you, okay, you gave me this prediction, now why did they give that prediction? Or is there a subgroup that's being missed here?
No, it's a great question. So, interpretability within neural networks is just a problem in general. So there's so many layers, and when I pass something from an embedding layer to a convolution layer, I don't actually know what that bright dot green means. The model's kind of learning it and learning that it works. And you can kind of back into it a little bit, and then you can kind of peek into the layer and say, if I put this word in and it gets very excited, you can kind of see that, but there's no way to go back and do like a feature importance for each token. So area of active research, I think is the short answer.
Is that something you have to do very often in the work or your team?
Yes and no. I think it goes back to the other question around, it's like a business decision, right? If you're building a model that writes, headlines that are clickbait and people click on them, you're good to go. If you're reading a medical record and people might die because there's some recommendation, then you definitely want to, you want to make sure that you're supporting it with real evidence and kind of investigate what's going on. So, thanks. Yeah.
I noticed you used the dropout of 0.5 after your embedding layer.
Yeah.
I was wondering, except from the reason that trial and error dictated that the best way to do it, do you have any other insight into choosing the dropout percentage?
Yeah, sure. So the question was, I used dropout here, and I picked 0.5 as the parameter. So first dropout, I didn't really cover it, but basically it takes the layer before it and it randomly throws away some data. And that's actually a good thing because then your models don't overfit, and it finds more than one way to figure out if something is positive or negative because each time it's kind of losing something. And then the question was, I picked 0.5, which shows like half the information, and that's just parameter V2. Usually somewhere between 0.2 and 0.5 is going to hit in the sweet spot, but you're just going to training.
Does it depend on data? Because if you're doing embedding, you have like 2 million vectors at one point, or even 15, or more than that. So does it depend? Does it scale with the data?
Yes, I think it's probably kind of like a decay thing. In that once you get to like a million words thing limit, you're probably fine just to kind of tune it. If you have a small data set and you put drop on it, you're actually throwing away a lot of information. So 0.5 is like way resistant if you only have 50,000 samples. So that's why I can include it in the MDB. Yeah, so the question is, does the dropout get rid of local movement? And basically the idea is that you're kind of throwing away some information, so could it be smoothing the cost function that you're trying to learn? I think the answer is yes, it probably does. Like with any regularization, it's going to smooth what you're looking for. If you're really interested in smoothing the cost function, the way to do that is to actually build a skip connection. So if you guys have seen the ResNet ImageNet model, they create this really deep model, but then they'll connect like the top layer to like 4 layers down. And then that allows them to kind of pass error information back up the chain and build a really deep model while still being able to propagate the error up. So what I would do in that case is probably take my convolutional layer and then skip the LSTM and then put it into the last layer and then allow it to kind of learn both the LSTM and go over.
Thank you for the last question. So you consider using a model where you have vectors, LSTM, all samples, paragraphs.
Sorry, can you repeat that last part?
When a model, so your model your words at vector.
Mm-hmm.
Do you consider a different kind of model where you call sentences or paragraphs? In our solution,
Yep. Cool. Yeah, so I think the question is, have I looked at not only creating word embeddings, but like sentence or paragraph embeddings as well? And the answer is yes. There's a thing called hierarchical attention, which instead of looking at your whole sequence, it just looks at each sentence and then creates an attention vector for each sentence. And then it basically does the same model on those attention vectors. That tends to get really good results. So you could employ that. Again, I think it's, if you have a lot of data, it's good. If you're just doing it on an IMDb, probably not a good idea. The other thing I'll mention too is that you don't actually have to, you can go the other way in that you can create character-based embeddings and just tokenize every word into individual characters and then feed that sequence in. So that's another thing that works well if you have a lot of text where you're getting new words that you've never seen before and you don't have an embedding. That's a way to get around it. Yeah?
Thanks for the presentation. One of the popular applications of NLP is classification. So for example, if you want to know about sports news and online classes, so it's kind of like an unsupervised learning that's happening there. So how can we use these models again use them to unsupervised learning without having how can we get
So sorry, is the question how do we use classification of news stories in an unsupervised way, or?
Yeah, because one of the applications of unsupervised learning is to classify news articles that are streaming at real time. So is there a way in which we can use this model for some unsupervised learning?
Yeah, and sorry, and you mean this model, meaning the model that we talked about?
Yeah, deep learning.
Yeah, sure. So I think the ultimate thing that a deep learning model is going to allow you to do is push data through it, and then at any point in this thing, you can come up with a feature vector that essentially summarizes that piece of information. And usually that feature vector is better than doing something like TF-IDF or whatever we would normally do. And so you could create a language model just on all news data, and then cut it off at a certain point, take that feature vector, and then throw it into your classification model for the category of news or whatever it is that you're looking to do. And assuming your data size is big enough, you're going to have a pretty good result. Does that answer your question? Okay. Yeah.
So how do you know if the model is either overfitting or getting bad?
Yeah, great question. I probably should have talked about that. The short answer is that in addition to your training data, usually you train with a validation data set as well, and in addition to training and test or dev set. And so you pass both of those in when you fit it, and it'll plot the loss for both the training set and the validation set.
Right, but I'm also concerned about the evolution of language. Like people now use more LLL, and emojis, and yes to represent the field.
Yeah.
How do you accommodate this, like the evolution of language?
Yeah. Other than retraining, there's a couple of different ways that you can deal with out of vocabulary words. So one is a character model. So breaking things down into to characters versus words. And then another is that you can actually have two embeddings layers, one for words you know, and then one for words you don't know. And that can work in some cases, and in others it doesn't really work. So it's tough, is the answer. Yeah.
Have you done this with like agglutinating languages or affixing languages?
I'm sorry, I'm not familiar with either of those.
Oh, sorry, it's just random, like Turkish or I think you mentioned Mandarin. And
yeah, I haven't personally. I usually work with English, but if you're interested in that, there's a really good paper by Google about essentially translation, and they create the representation in English, turn it into a fixed size vector, and then use that to create the translation into whatever language you're going to. But rather than creating an English to Turkish model or English to Mandarin model, they create like a 5-language to 5-language model, and that seems to get really good results and a really good representation of the vector. I'll dig it up and try and post it in the Anything else? Okay. Thank you.